All right, our next unit is on energy, and it'll be the intro to the topic. So we're going to have energy nested in a whole bunch of our topics as we move forward in physics, but this will be our first and our starting point to understand this concept. So the three big words we're going to look at are work, energy, and power. So energy is a concept we're familiar with. We've heard about it from a very early age, but we can still be perplexed by it, and it has some tricky elements to it. So there are things we know have energy, like a hot fire. We can feel that kind of heat radiating from the fire. We can see a moving bus and say, well, that must have a lot of energy. It's moving quickly. So there are things we have an intuitive sense of that have energy. Where we sometimes have difficulty in this unit is seeing how energy transforms and how energy moves throughout a system. So big idea as we move forward in physics is that everything has energy and everything's made up of energy, and we're going to refine and modify our thinking about this topic as we move through grade 11 and grade 12, both in physics, chemistry, and biology. It's woven into all of them. So please keep an open mind. What we talk about today will evolve and get more complicated or more dynamic as we push forward. So the first big idea we're going to do in the grade 11 course is this idea of work. So work's a term that we use in our everyday life quite a bit. In science it has a very particular meaning. So we're going to reference or talk about mechanical work, and it's work done by applying a force over a distance. So this is going to tie together both our kinematics unit and our force unit. So this is a nice merging of those pieces that come together really nicely in this section. So for us, work is going to be a force applied over a distance. Okay, so to calculate this concept, it's a scalar. This is really important. It's a scalar, even though both force and displacement are vectors. When we multiply them together, this is going to be a scalar product. We're just going to end up with a magnitude. There's no direction, which seems a bit strange right now. We'll return to this in calculus if you carry on to that course, but it's just a scalar result. So there's no direction on this. And the SI unit of work is a Newton meter, and it's called a joule. And again, it's one of those derived terms. It's made up of other terms, other values. And in the beginning, it won't have a lot of meaning to you, but as we do more problems, you'll start to get a sense of what exactly a joule is and what's a large quantity versus a small quantity. But it takes a bit of time. Okay, so we look at something like this. A new weight training program is based on the amount of work you do in a workout session. Okay, so we have three options here. And let's just grab we'll grab this pen right here. Pen, come on, there we are. Okay, so training plan 1 involves carrying a heavy weight of 50 kilograms up a flight of stairs that rises 5 meters. So I'm just going to convert that 50 kilograms. I'm going to use 10 for gravity. So I'm going to have that takes a 500 Newton force. So if I use a 500 Newton force to carry this heavy weight up 5 meters, and I use my work equals force times displacement, then that's going to lead to 500 times 5, and that's going to be 2,500 joules. Okay. The training plan number 2 involves carrying a medium weight of 20 kilograms, so I'm going to say that's 200 newtons up a flight of stairs that rises 12.5 meters. And again, if we multiply those two together, what we should see is we get the exact same amount of energy used, 2,500 joules. Training plan 3 involves carrying a light weight of 5 kilograms, so I'm going to say that's a 50 Newton force up a flight of stairs of 50 meters. And again, if we multiply those two together, we get 2,500 joules. So which training plan involves the most work? Well, the reality is they all have the same amount of work. Okay, they're just done in different ways. And this is going to be one of the benefits of talking about this unit, is we can see that you can apply a large force over a short distance or a small force over a long distance or displacement and come up with the same amount of work. We see this idea when we talk about ramps. So A ramp's a simple machine that utilizes the work equation. So a ramp increases the distance traveled, which results in a smaller force required. So you have a choice here. You could lift this guy right here, 100 newtons over 2 meters, you would end up with 200 joules. Okay, or you have something like this one over here, and we won't go into how the forces break down or the angles. We don't need that right now. But if it takes a 20 Newton force to push this box up this ramp, and I have to do that for 10 meters, that means that's going to require 200 joules of work as well. So both have the same amount of work done. They both get the box to the higher level of 2 meters, but how they do it is different. Okay, so one is a short distance with a larger force, one is a larger distance and a smaller force. Okay, if you've ever seen a wood screw or a bolt, just from an interest standpoint, a wood screw is basically a ramp that's been wrapped around an axis. Okay, sample problem. I'll take a shot here. A curler applies a force of 15 newtons on a curling stone and accelerates the stone from rest to a speed of 8 meters per second in 3.5 seconds. So a couple things. We have a force here. We also have some values that could be used in kinematics. So I want to keep that in the back of my mind. Assuming that the ice surface is level and frictionless. Okay, so that's another important piece of information. If I have to draw a free body diagram, then I know I'm not going to need that force resisting my motion. How much mechanical work does the curler do on the stone? So as soon as I see mechanical work, I know I'm dealing with force times the displacement. So I'm going to go back up into the kinematic side, and I'm going to jot down a couple of my kinematics. I start from rest. My final is 8 meters per second. My time is 3.5 seconds, and I'm looking for a D. Okay, so if I have D equals, I can do the average. There are other ways to approach this, but this is one option. So if I plug in all of that information, I know this is 0, this is 8, so 0 plus 8 divided by 2, so I have 4 times 3.5, so I end up with 1214, I believe. Let's just double check. 14 meters. And now if I go back to my work expression, I have a 15 Newton force applied over 14 meters. So the mechanical work done is 210 joules. Okay, here's a practice question to try on your own. So if you want to hit pause here, and then we'll take it up real quick. Okay, so let's go have a quick look here. We have a 0.5 kilogram laboratory cart. Initial velocity 3 meters per second, accelerates for 2 seconds at 1.2 meters per second squared. So there's some kinematics already showing up. Assume there's no friction, so calculate the net force exerted on the string on the cart. So if we wanted F net, we know that F net is mass times acceleration. So we have our mass and we have our acceleration, so we should have 0.6 newtons is the force exerted on the cart, and there it is. Calculate the displacement of the cart. So again, we're going back to some sort of kinematics here. So let's go initial velocity 3, acceleration 1.2, time 2 seconds, and we're trying to find D. So if I go D equals VIT plus 1/2 AT squared, then D equals 3 times 2 plus 1.2, pardon my messy writing, and then I get my D, so I'm going to have 6. I'll just calculate it real quickly here. 6 plus 0.5 times 1.2 times 4. I think I get 8.4. I'll just do a quick check on that. Oh, gotta go turn to eraser. There's my 8.4 meters. And then calculate the mechanical work done by the string on the cart. Okay, so now again, work. We have F, which we have D. So if we take our work 0.6 times 8.4, should be about 5 joules. Okay, and there we are. Now a couple of things to note. What happens when the force and the direction of displacement are not in the same direction? Okay, so we're going to bring back that idea of components. So there's a couple of things I want to highlight here. Okay, so Fn, Fg, and the force vertical here. All of those are working in a vertical direction, but you'll notice the displacement of this bag is all horizontal. Okay, so what we end up looking at is just the horizontal force and just the displacement work together. Okay, so take a second and review those sine and cosines on how to resolve those components. That might be a bit rusty. And what we do is we now modify our expression. Okay, so instead of just saying work equals force times displacement, we now add the cos theta in there, which is going to be the angle between the force and the direction of the displacement. So that theta right there. And all this is just saying this is the x component. It's a fancy way of saying it. Okay, so here's a quick problem. I'll give you a second to try it if you like. Okay, so we have a vacuum cleaner. There's a force at an angle. Okay, so right away we know there's going to be some sort of cosine involved with this, and so work is going to be, there's a 50 Newton force applied through a cosine angle of 30 degrees. Pardon me, that's a little bit sloppy. And over a distance of 3 meters. So make sure your calculator is set in the right mode. Make sure it's cos 30 and not sine 30, and you should end up with 130 sorry, not newtons, joules, 130 joules, my bad. Make sure I get those right. So 130 joules is the work done. Okay, I won't write much for this one. This is more of a reading question and a discussion question. So if this young person here moves at a constant velocity, that means the net force acting on this person, in particular the backpack, is 0. So if there's no unbalanced force acting and this person walks forward, what we end up with is a case that actually has 0 mechanical work done. Okay, everything is in opposition, it's all balanced, so as long as this person walks at a constant velocity, isn't jumping up and down, this is a case where there's actually no mechanical work is done. And that's going to be a little bit strange because you know that a heavy backpack feels heavy and it feels like it takes a lot of work to move it, but from a calculation side, this is a 0 work case. Oops, jumped one too far. Let's back up. So here's 2 questions to try. I won't take these minutes up in the interest of time, so pause it, take a try at it. Okay, so you've had a chance to try it. What I do want to highlight is just at an angle of 40 degrees below the horizontal. So what that means is if this is the lawnmower and the person is pushing on it, this could be the horizontal and this is 40 degrees. Okay, so hopefully you had a chance to try that. Come up with 1,150 joules or 1.15 kilojoules. Second question, a father pulls a child on a toboggan along a flat surface. The rope's angled 35 degrees above the horizontal. Okay, that's a little bit more traditional. So if this represents the sled, there's the force. 35 degrees would be buried in there. The total mechanical work done by the father over a horizontal displacement of 50 meters is 2,410 joules. Determine the work done by the toboggan, by the normal force, and the force of gravity, and explain your reasoning. Okay, so the work done on the toboggan, that will be your work expression, so that'll be work equals F cos delta D. Plug in the information, come up with the numbers. The ones that normally get people are the normal force and the gravity. Remember, those are both at 90 degrees to the displacement. If you take the cos of 90, you'll see it's 0. So neither one of those forces can actually do any mechanical work in this situation. Okay, so the normal force and the force of gravity do zero work. Okay, so is work done when a force fails to displace an object? In short, no. When you have this delta D here, this delta D right here is zero. So if that goes in, it doesn't matter how hard you're pushing on that wall, that car, whatever it might be, if it doesn't move, no mechanical work done. Work is done. So this is work equals zero. Right there. Okay, positive and negative work, parts versus system. So sometimes it's really important to look at what forces are doing individually within a problem. So if you look at this one here, there's a force that's going to lift this box up. Okay, and then there's a force of gravity that's acting in the opposite direction. So now you can analyze the force here, okay, of the lifting or the applied force, and you can say, well, it's 15 newtons over 2 meters, that's 30 joules of work. You could also look at the gravity expression. You'll notice it's got a negative in it because it's in the opposite direction. So now negative 12 times 2, that's negative 24 joules. Okay, so and if you looked at the total work, you'd see 30 minus 24 is 6 joules. Okay, and those of you who are looking really closely at this, you'll also say, well, the F net in this case, by the time you do 15 minus 12, the F net here is 3 newtons. Well, 3 newtons times 2 meters will get you that same 6 joules. Okay, so that's going to be one of the things we're going to look at. There's going to be a net force that does work, but you can also analyze the parts to see what they do individually. Okay, so pause it here and have a look, and we'll try these and then I'll reveal the answers in a minute. Okay, so first one, Curtis pushes a bowl of cereal along a level counter, distance of 1.3 meters. What is the net work done on the bowl if Curtis pushes the bowl with a force of 4.5 newtons and the force of friction is 2.8? Now we could set this up. Here is the bowl. Here is 4.5 newtons. Here is 2.8 newtons. And we could do these individually, or we can say, hey, there is a net force of 1.7 newtons acting on that cereal bowl. And if I take that 1.7 and I times it by 1.3, I should get something close to 2.2. And we'll just double check. And we get our 2.2. Cool. Second question, a crane lifts a 450 kilogram beam 12 meters up at a constant velocity. Calculate the mechanical work done by the crane. So in this case, you could have the crane, again, there would be some applied force, and there would be some Fg gravitational force. Now it didn't ask for the total force or the net energy used here, it just asked about the crane, and that's one of the things we'll have to really isolate is what is this question asking. So it's just asking about this one here. So I'm going to say it's 450 kilograms. I'm going to say that's about 4,500 newtons just for the interest of speed, which means my applied force is going to be the same because it's moving at a constant velocity. So if I take my 4,500 and I multiply it by 12 meters, okay, then I got 54,000 joules, so 53 kilojoules. That's pretty darn close, mostly due to rounding. Okay, then last little bit here, graphing work done, positive and negative values. So we can plot work done, we can plot them as a positive graph, we can plot them as a negative graph. Just like we had in kinematics, we have different types of graphs. This is a force distance graph. Okay, so the area of the bar graph is the amount of work done. So just like we did way back in kinematics. Okay, and then again, you could take your positive work and your negative work. If you add those areas together, it can tell you the net work done. Okay, we won't have a lot of these in grade 11, but just so we talk about it, you can have a force that is not constant over the entire duration of the problem. Okay, so you'll notice down here the force is 0, but up here we have some sort of F max. So if we said this was, let's say 10 newtons, just for ease of calculation, and this was 0, the average of those would be 5 newtons. Okay, so if you can think of this rectangle coming down and filling in here, so this piece right here. Could come down and fill this in. So basically we're finding the area of that green triangle. So it's still the area under the curve. It's just a triangle versus a rectangle. So the area under the triangle is the amount of work done. And that's for when a force is changing within a problem. Okay, lastly, a couple questions to try. So section 5.1, 1, 2, 3, 7, and 8. Apologize for some of the slip-ups, but it's late at night. And there you go. Thanks for listening.